All right, let us now work through this page of definitions here. So it says some definitions. First, sequence. What is a sequence? It's a list of numbers that can be written in succession. It can have a pattern or be random. We focus on rule-based sequences. The numbers in the sequence are called terms. So if we look here, for example, 2, 4, 8, 11, 14, all of these are what we call terms. So each of them is a term. And now I want to zoom in here for a moment and see how these two things are different. If I was to ask you to figure out, how is this changing from each one? Hopefully you could say, well, each time we're plussing 3. 2 plus 3 is 5, plus 3 is 8, plus 3 is 11, plus 3 is 14. That's what's happening there. This is what we call linear growth. Linear growth. So it's linear. Here, on the other hand, we're going from 10 to 12, 12 to 14.4, 14.4 to 17.28, and 17.28 to 20.736. What on earth is happening here? Obviously, it's not going up in a linear fashion. It's going up in another way. This is what we call geometric. Geometric is when we have, and I'll write it down, geometric. Geometric is when we are either multiplying or dividing to the next term. The way that we can determine what it is here is we can go 12 divided by 10. And if we do that, I'm going to end up with 1.2. So that means I'm timesing 1.2 each time here. And you didn't have to do the first term. You could have done any term. So for instance, I could have taken these two numbers. I could have taken 20.736 and divided it by 17.28. And I would end up with 1.2 again. So each time, the way I'm increasing is geometrically, which means by multiplication. And of course, the inverse of multiplication is division. So you could say it's either 1, but most of the time, well, not most of the time, sometimes it would be division, won't it? All right, let's go growth. That's geometric, and we'll be seeing more of that soon. All right, let's keep on rocking on here to the next one. The next one we have is recursion relation. Recursion relation. So an equation representing a sequence. It must contain a start point. The first term, u of 0. It also has to contain a rule linking successive terms. And this is what it's going to look like. We'll see it soon. And n represents the number of iterations or applications of the rule. Let's look at an example here and see how all these components are going to play a part. The first thing that we need is this. This is our starting point. So let's write above it. It's our starting point. Hopefully you can write nicer than me. I'm going to try that again. Come on, n. Don't fail me now. All right, so it's going to say starting point. This is where we're starting from. It's saying we're starting at 2. A of 0 is equal to 2. And then the next thing is going to tell me it's a rule linking successive terms. So this here, what this represents is my next term. This a of n represents my current term. And then obviously here I just have a plus 3. So you can see that this is going to be a linear rule. And what it's telling me is we're going to start at 2 and we're going to add 3 each time. So if we were just to visualize this for a moment, it's saying a of 0, well, a of 0 is 2. It's our starting point. What is a of 1? Well, a of 1, I would put 2 into this spot because that's my current one and go 2 plus 3 is my next term, 5. How can I figure out what a of 2 is? Well, now I'll put my current term, which is 5 this time, into there. 5 plus 3 is my next term will be 8. And hopefully you can see how this works. So a of 3, well, what's my current term? My current term this time is 8. So I put 8 in here. And I would go 8 plus 3 is my next term, 11. So that's how it works. All right, perfect. My next one I've got here is a geometric one. So as you can see, it's saying we're starting at 10. And then I am timesing each term by 1.2 to get to the next one. This is my current term. This is my next term. Hopefully you can see that this and this is actually what we saw up here. 2, 5, 8, 11, 2, 5, 8, 11. And if we were to do this one, we're starting at 10 and I'm timesing each one by 1.2 to go on. So there you go. Hopefully that makes sense for you. All right, let's keep on going here. Next, we have growth. What is growth? The relation, a recurrent relation is modeling an increasing relationship. So if we have a recursion relation and it's increasing, it's a growth one. Decay is when the recursion relation is modeling a decreasing relationship. So in other words, it's going down. My common difference, commonly denoted as D, is a constant amount that is added or subtracted. So that's a common difference. When a common ratio is commonly denoted as R, and a constant amount that is multiplied. So it can be calculated using two consecutive terms, second term over first term. And that's exactly what we saw on our CAS when we did this. So see how we went second term divided by first term? So just to recap this idea of common difference and common ratio, my common difference when we're looking at our linear growth would be when we're plussing 3 each time, when my common ratio is when we're multiplying 1.2 time. And as you can see, the common ratio can be found by going second term divided by the first term. Cool. We have linear growth and decay, so constant increase slash decrease. We've seen this before. This is exactly what we were looking at when we were going through this example here. So as you can see, it says each successive term is found by adding or subtracting the same value, the common difference, used to model applications such as simple interest loans and investments, and flat rate and unit cost depreciation. Creates a straight line, increasing or decreasing. Then we have geometric growth or decay. So geometric growth and decay, that's when we were looking at this one right here. So exponential increase slash decrease. Each successive term is found by multiplying by the same number, the common ratio, used to model applications such as compound interest loan and investments, and reducing balance depreciation. Creates a curved graph, increasing slash decreasing. As you can see, here are some examples of it right there. All right, that is some definitions that you need to have in your mind as we're working through this content.